Hello, my name is Igor Campos, and I have recently joined the Technology Innovation Institute in Abu Dhabi as an UAV engineer, and I will be speaking about faster or greater surveys through a method called camera auto mount pivoting oblique surveys. Just to put it in context, UASs are becoming increasingly more popular remote sensing tools, particularly in photogrammetry applications that yield digital elevation models, orthomosaics, 3D models, and point clouds as outputs. And there are even specialized manufacturers that create multi-camera oblique systems that have several cameras and lenses in the same platform, but they are heavier and thus have less platform compatibility, particularly with the lighter weight ones. But recently, there have been notable improvements in camera sensors, and particularly in the increased shooting speed. And we can even see this in our mobile phones. And since most rotary wing UASs already feature actuated mounts to keep the camera stable or to allow the user to point the camera where it wants, and this can also be added as a feature in fixed wing aircraft, why not capturing multiple oblique angles with a single camera in the same pass? And how can this increase the efficiency of UASs with the increased horizontal field of view of this arrangement? So essentially, we ended up defining a new MAVLink command that has adjustable row angle limits and number of positions as shown in the picture, where the row angle specifies how far the camera will move to the left or right of the center, and the number of positions is the number of pictures that will be taken at different row angles. The pitch angle for now is a fixed pitch angle that will remain for the flight, but could be further expanded in the future for allowing also varying the pitch in the same pass. This command was implemented in PX4 and also ArduPilot flight stacks. And support has been added in the QGroundControl. It's, however, pending the merge of the pull request. And essentially, it accounts for the gain in the horizontal field of view to calculate the traverse separation, allowing for the flight lines to be further apart than a traditional nadir-only survey, which translates in more efficiency, allowing the drone to complete a same mapping job faster or to map larger areas. The new command is the oblique survey command, and it's numbered as 260 to be easily related to the camera trigger by distance, which is 206. The first two parameters, the distance and shutter, behave the same as in the camera trigger by distance command. The third parameter, minimum interval, is the minimum interval in which the camera is capable of taking subsequent pictures repeatedly. The number of positions, it's how many positions will be taken across the row angle limits in which the camera will capture photos. The row angle is how far the mount will move to the left and right of the center, and the pitch angle is only a fixed pitch angle for now that could be further expanded in the future. For the Autopilot logic, both flight stacks had the same logic, and we ended up adding the blocks in green to the traditional logic that only verified if the camera triggering distance was toggled, and then it would trigger the camera, store the position and time information in the flight log, and keep repeating this loop. Now we check if it is the time to, if we already moved the camera, and if we haven't moved the camera, then we check if we are supposed to move it now, if it is over the minimum interval specified in the parameter, and move it accordingly, then reverting to the previous logic. Here are the height and overlap calculation. I don't want to go deep into this math. And essentially, it relates the height to the parameters of the ground sampling distance, the survey parameters, as well as the camera intrinsics. So this equation gives us the height and overlap data that QGroundControl needs to calculate the flight paths. We added this as an option in the survey panel of QGroundControl. And when it is enabled, there is a panel that allows the user to select if it is a 2D survey or a 3D survey. A 3D being more for urban scenarios where you have cannons and you want to capture the facades of buildings, and the 2D survey for open fields where you basically want a 2.5D information, being the position and height of each point, and the parameters that are described in the earlier slides. We simulated this in PX4 software in the loop simulator using the Sonoma Raceway scenario, as this scenario has a high accuracy 3D model that we could compare against our surveys to see if they produce comparable outputs with the same quality. On the left, it was done with the Campos method, and on the right is a traditional nadir-only survey. And it is clear that the traverse separation is larger on the left side than on the right side, and thus the drone had to fly much less with the Campos method than with the traditional nadir survey. Another thing that we notice is that there are more photographs in a same line. And this is because we use the front lab parameter such that two subsequent photos pointing in the same direction will be within the range of the specified front lab. So the camera will be moving left to right. So in this survey, it was 3 positions. So it would take a picture to the left, a nadir picture, and a picture to the right. Both pictures that are pointing down would be within the specified front lab, just as in the right survey. To perform the simulation, we spread ground control points in this model to allow the photogrammetry software to identify them and compare the accuracy with both techniques. And the root mean square errors for both methods are here and in the same order of magnitude, with slight better performance for checkpoints in the Campos method, but quite similar accuracy for the control points. In image overlap, despite having less lines, we can see that the overlap is greater in the Campos survey than in the nadir-only survey. This is interesting, and this is actually because this is a challenging data set where this part where there's lower overlap in green and yellow tones is solely grass, and in the simulator, grass has very low texture, and the photogrammetry software has trouble aligning these images. But the oblique images from the parallel lines that are close to the lines in this more challenging area contributed for a better alignment and better overlap. This was surprising and a nice discovery. As I said, the area with only grass failed to align properly in the photogrammetry software, and we can see that the hole is larger in the nadir-only survey when compared to the Campos survey. However, when we fit the Gaussian curve to both surveys to the cloud to model distances histogram, then we observe that they are in the same order of magnitude, and I wouldn't be able to say if one is more accurate or better than other, because both the standard deviation and the mean of the distribution are very close. Then we finally compared the distances of both point clouds, eliminating the points that were not suitable. So we limited the distance to 20 centimeters here. And there's a histogram to the right of the legend. And it is noticeable that the majority of values are around 5 centimeters or less in distance, and that was the target ground sampling distance for this survey. So the distance between both models is within 1 time the ground sampling distance, which is quite good actually. I also performed a field experiment where I spread ground control points in an urban area with various characteristics. There are streets, there are fields, there are parking lots, there are taller buildings, houses, and trees. So it's a very diverse scenario. And we tried to spread the ground control points as evenly as possible. The root mean square for both methods are displayed in this slide. And again, we see that they are quite similar with better performance, particularly in the Z for the checkpoints with the Campos method than in the nadir one. But besides that, everything is similar. There is slightly better control point performance for the nadir, but the checkpoints are what matter most, and they are actually pretty close. The GSD was also set for 5 centimeters. Here are the overlaps of both methods. And again, we see larger separation on using the Campos method on the left. And the photos, the flight lines are closer with the nadir survey. And even on the right side, I would say that it would have benefited from another flight line here. So in the nadir one, it got 9 flight lines, and in the Campos 5, which was an 80% efficiency gain. But if this other line was present, it would translate in a 100% gain because the numbers are small. So this additional line would represent 20%. But it was the same polygon, and this is how the QGroundControl assigned the flight path. So to keep things straight, we didn't manipulate the region to increase this other flight line, which would make it more comparable overlap-wise. As we didn't have a model to compare against, we could only compare the distances between the Campos and nadir surveys, and we limited to 1 meter. Again, this is a real-world experiment, so the leaves of the trees are moving obstacles. There are parked cars on the streets that are in one flight and there are on the other flight. So we expect a bigger difference, but the vast majority still remains below 15 centimeters, which is 3 times the GSD. And considering that the camera is a GoPro camera with a fisheye lens, not the best quality, this is actually a very nice result. And for future work, I hope to evaluate the efficiency gains for 3D surveying missions, which should theoretically be even higher than 2D/2.5D surveying missions, and maybe varying pitch, but this needs faster cameras and mount actuators to be able to perform surveys in an efficient manner without reducing the vehicle speed. And in conclusion, this is a novel surveying method that provides higher efficiency. We demonstrated 80% gain in field experiments, and there is a theoretical gain of 100% or greater. This depends on the camera intrinsics, on the focal distance, and other parameters. It is essentially a software-only feature, so it's free or a very low-cost upgrade for platforms that do not have an actuated mount in the roll axis, which is something that can be employed in fixed-wing aircraft. You can just add a servo to hold the camera in the roll axis, and then you move it left to right, and this method would apply for these vehicles. So it's very easy to adopt and open source with code written for PX4, ArduPilot, QGroundControl, as well as a new MAVLink command. There is an open access paper available, and it's titled Towards More Efficient UAS Data Acquisition, Camera Auto Pivoting Oblique Survey. It's available at this link, and I can share it on the chat. And now I am available for questions and answers. So Ben, in the field experiment, I limited the GoPro field of view to take 7-megapixel images because I wanted to simulate a camera more similar to what people use in surveying scenarios and reduce the degradation induced by the fisheye lens. So I actually used a narrower field of view. This is something that is configurable in the GoPro camera. So it was, if I'm not mistaken, 7-megapixel images for the GoPro. However, in the simulated one, I think it was 12 megapixels, if I'm not mistaken. I think it was 4,000 by 3,000. It is a simulated camera, and I could change the parameters in Gazebo as I wished. Yes, if you use a narrow field of view, it should work well. I particularly like the 20 millimeters lenses for mapping. There are some people that prefer the 16 millimeter, but I think it gives the field of view is too wide, and you get degradation in the corners. So I prefer the higher quality of a narrower field of view. Thank you, Burkhard, and thank you, Ben. Let me see something that people also asked me. Let me go back a few slides here. So how does this increase the efficiency? Essentially, we have a wider field of view when we add this oblique images. Is like if we are actually capturing data of a broader area. And there are comparable solutions from other manufacturers. There is the SenseFly Soda camera, the 3D camera they have, but the main difference that I identified is that they don't account for these gains in the flight planning software. And this is what we did in QGroundControl. We actually account for these gains so that you don't need to use different overlap or front lap or side lap values for this setup. You use the same values that you are using to, and the software will adapt according to the row angle parameters that you specify. I will be sharing the link and give me a second. I have to copy it, and then people can access the paper if they wish to. Okay, hey Julian. It really depends on the speed of the vehicle and the number of parameters, but you can actually decrease the front lap a bit because you have pictures pointing towards the side that will be aligned with the nadir picture. And I would say if the camera is capable of 1 FPS or 2 FPS, which is well within the range of modern cameras, then it's reasonable to use this method. It also depends on the ground sampling distance and number of factors, the resolution of the camera, the lenses. So it's hard to say, but from my experiments, it was reasonable for 1 FPS or faster cameras. With the key thing being that it must be for continuous shooting. So when you go in Sony's website, you likely see the burst FPS specification and also the continuous FPS, and that is the one you want to focus on. Of course, you also need a fast memory card to achieve the speed specified by the camera manufacturer. Otherwise, you will have a bottleneck in your storage. But it should be sufficient with modern cameras. Yes, I would say so, particularly with the latest cameras that use it. I focus it more in Sony cameras, and I've seen numbers of 5 continuous FPS up to 10 continuous FPS. So it should be sufficient. Oh, and Julian, I should thank you for your support and a review of the code and support in the developer calls. And everybody in the community was very friendly. It was pretty straightforward for me to get this merged and working in the firmware. So you've been great, the community. And I hope to get a chance to work in further projects together as I join the TII. So I guess this is it. We are running out of time. And thank you for your time and for watching this presentation. Yeah, I just have to talk to Dan to get this merged in QGroundControl, but you can just try it from my PR. Thank you. Oh, and it's actually quite funny because there's a big brand with 3 letters, everybody knows, that has released this year a similar feature, but it's nice to see that the open source community actually developed something before them. All right. Thank you all for your time and for watching the presentation. Thank you. See you. Bye-bye.